let's continue on the topics, and this one is follow up our textbook, section 1.4. So here is the I would say the very formal discussions into the topic about vibrations. So what is vibrations? Basically, vibration is oscillations and repeated motions. Okay, and that is the fundamental concept. And using this graph as one example, if we kind of pull the mass a little bit and release it, if we release this kind of pulling, basically due to the distortions of the spring, then the thing is going to oscillate. And if we project the vertical displacement over time, then we will have the curve like this. And later on, you would learn this curve will be kind of the sine curve or cosine. Basically, that's the sinusoidal functions. And another feature of vibration is this is a repeated motion. Repeated motion, basically, they have period. Okay, so inverse of the period basically related to frequency. And so there's a one term here kind of the introduced to you is we're going to learn the frequencies of vibrating systems. Okay, and we have two kinds of the frequencies. And one is we call the natural frequencies. And natural frequencies just like the fingerprint to the system. Once we have a spring constant and the mass being defined or given, then the natural frequencies are already given there because that's the properties of the parameters of the system. And the other frequencies is, say, if I pull this mass with my hand, if my hand is a 4-bar linkage, I try to vibrate this system with arbitrary frequency I defined. So this such externally applied loading frequency we call the working or loading frequencies. Okay, so loading frequencies are kind of given by, say, engineers or by users. They are different from the natural frequencies, which is the intrinsic properties of the system. Okay, so from here, you should know about this one, and you will learn. And the last features about the vibrations is this. You see this called the A, amplitude. Amplitude representing is the maximum displacement of the vibration systems. Okay, so basically, if we describe the vibration repeated motions can be described by a sinusoidal functions. Basically, amplitude representing is the magnitude of that sinusoidal functions. So, for example, and so say right now without rigorous mass, let me say this one, say x of t. So, for example, say if we start in describing the vertical displacement using x. So, for example, say let me describe x can be described say by sine omega nt plus v. Okay. So this is a very broad, very general description of vibrating systems. And omega n is called the natural frequencies of the system. And A is simply we call the amplitude of the vibrations. Okay. And this V is we call the phase angle. The phase angle sometimes, so if say sometimes you started from this moment as the time 0, so basically phase angle telling is the lacking of this or somewhere. Different textbooks have a different definition of the phase angle. Basically, in general term, phase angle simply tell is the kind of the peak from the peak of the initial term to away from where you're going to start describing. So basically that is kind of phase angle. And in our textbook, I will try to stick with all the notation with our textbook. So whenever later on appropriate, I will find a very precise, I will provide you a very precise definition of the phase angle that is given by our textbook. And from that moment onward, we simply stick with the definition of our textbook. Okay, but in general, again, in my learning is I know the phase angle basically is this one describing somehow lacking some textbook defined is by this, some textbook is defined by some I would say something like this one depends, really depends on the user's preference. So those ones from here, basically that kind of give you the certain terminologies and the concepts. Another things I want to describe is this. This is a very critical concept, and you have to take it today. We compare two different descriptions of the vibration systems. So say this is a spring, and then you say the spring constant K, this is a mass. Basically this one is, say, I describe the displacement of this mass, for example, from a position. For example, at this position is initial, there's no displacement, no initial velocities. So basically this is on his own naturally equilibrated position. So basically we call this is, this system is on his own equilibrium, okay? So starting from the equilibrium positions or status, we describe the equations, the displacement here. Okay, so this is for the system that is going to vibrate horizontally, no gravity going to involve. So that is very natural. If we don't touch, if this spring doesn't deform, and if there's no initial velocity, basically the system will stand there initially stationary in motionless. So we're starting from here, describing the displacement. Compared to this system, if we have the system that's going to hand vertically, and in that direction, gravity applies. Okay, so we see what happens. So again, we're using the same mechanical components that's the spring, and we have the same mass of the block. Okay, so right now the gravity is in these directions. Hold it down. For these settings, initially, let me say I use my hand to hold the mass, okay? And now you just listen. And I use my hand to hold the mass, and then holding it such that the spring doesn't deform. So under this situation pretty much is the same as this one. The spring doesn't deform, right? And no deformation on the spring and no initial velocities. So basically this setting is the same. However, my hands kind of get sore. I don't want to kind of keep my hands here. So I will gradually release my hands away due to the weight of this mass block. And this one going to deform a little bit. So let me say, due to the gravity pull, the mass move from here to here, right? That distance is representing the deformation of the spring to overcount the weight. So under that situation, let me call this is called the delta. So the displacement delta such that K times delta equal to the weight of this mass block. And again, when I release my hand, I say I slowly remove my hands, not to cause any oscillation. I just slowly, we call the, in more precise term, is we call the quasi-static loading process. So quasi-static, that means the process is very slow, barely is naturally zero. Okay, so I slow it down here. So under this situation, the system right now is become to this. So let me redraw the systems in its equilibrium like this. So let me level the positions here. So this is where the spring hangs. And right now the spring stretches a little bit, and now the mass staying here. Under this case, this is on its own equilibrium after balance with the gravity. Good? So this is called the equilibrium. EQUILIBRIUM. Okay, so the same thing, this is the equilibrium positions. Okay, so from here, can you tell the difference between the two configurations? So in this way, we have the equilibrium positions that has been taken into account of the balance with the gravity. So from here, we call the oscillations or vibrations is to respect to the equilibrium positions. So that means if this spring going to vibrate, if this mass going to vibrate, say for example is vibrating range will be something between here and this is the middle line and representing equilibrium positions. So this is called the amplitude here. This is the amplitude. Okay, compared to this case, this is the equilibrium positions here. Okay, so this mass going to oscillate up and down, up and down. So for example, the range is in this way here. So again, this is called the amplitude. You good? Okay, so basically here the very first important concept is the vibrating systems are going to repeat its motion respect to its equilibrium positions. So that means it's kind of the center of the displacement located right at the equilibrium positions. Okay, and for the system with the gravity, you have to take out the influence from the gravity. Okay, so again, later we will have more. I will bring back to here. Okay, so here I'm going to introduce more about what is the vibrations. And again, right now everyone got the concept. Vibration is the repeated oscillations, periodic motions. And then basically the repeated motion or oscillation is due to the transformations of the energy between the kinetic energy and the potential energy. The potential energy in particular is to describe the strain energy stored in the spring. Again, once we want to vibrate, we have to displace the mass a little bit and release it. Once we displace the mass, we deform the spring, right? So how much the spring is deformed depends on how much you're going to pull away the mass block from its equilibrium positions. So it really depends on you. The more you pull it, then the more energy of the strain going to obtain, the spring going to obtain to obtain. So in this way, you create the deformation of the system, which means you provide initial positions. That means you provide the initial position x0. So that means, say, you pull the mass block from his initial equilibrium positions to here. Okay, so for example, let me say this is the x0. Okay. So if you put this mass block to this position, you release it, then it's going to vibrate, going to oscillate. Okay. And this amount you can decide with the initial position. Okay. Even more general is this: you pull it so quickly such that you also create a certain initial position velocity. So in general, you can provide initial position and initial velocity to a vibrating systems. Then under that situation, whatever the spring going to responding to such initial conditions, and then the system going to vibrate. So once initially the spring has deformed and it creating the potential, and the spring have a potential energy, and in a way that the spring or the elastic object going to deform, going to recover back to his initial undeformed status. So that means going to recover, they basically begin to have the mass block going back. So basically the build up between the potential and kinetic energy, the energy kind of transform into two forms, and that is the way the oscillation is going to start with, and I would say start the oscillations. Okay. So that is the second point here. And ideally, we have the vibration system just like this. Only have a spring that is for storing. That is a symbol for storing the energy, in particular strain energy, and the mass is representing a symbol for the kinetic energy. That is motion. Okay. But in practice, all the systems have the friction. Okay, friction, that means damping. And what is damping? Damping is to dissipate the energy. So in practice, in a cycle of the energy transfer between the two types, a little portion of the energy going to dissipate through friction. And this kind of dissipation is one way. It's not reversible. So once we dissipate it, it's no way. Well, in terms of mechanical sense of view, we assume once the energy dissipated through friction, there's no way to recover or harvest back. But I know from the thermal science, the thermal system, you have a way you can harvest from the heat, right? So, but we don't talk about that one. So here we have gradually the energy going to dissipate. So eventually the total energy of the system is actually decreasing over time due to this. Okay, so eventually in practical systems, the vibration is going to stop at somewhere. Okay, so that is the things here. And one example is here showing is a single pendulum. So single pendulum, for example, here assuming this string is rigid and no deformations. So here, basically this little mass ball is following a trajectory that defined by the string, the length of the string. So for example, initially we kind of disturb this to here, and then we release it. Basically, that can do back and forth and begin to oscillate. Okay, so so that is one simple example for this. So that is about this page. And now we're going to learn formally the symbols. We're going to describe mathematically vibrating systems. Basically, this is the symbol we're going to use, and this one is called the mass. Okay, the mass, again, that is a component for describing the kinetic energy. And this is a spring constant, and we're using K. Sometimes, if we have a multiple springs, then K1, K2, etc., using kind of the notation. And this is called the damping. Damper, okay. So damper, you can see this kind of the drawing, just like drawing the piston. Okay, the piston, that means kind of the repeated motion, and inside there's a fluid. So damper, basically using, sometimes we're using the notation C, and I don't know what is the original reasons, but the many textbooks using C as a notation for damping. And so basically this component representing is the dissipations of the total energy, okay? And from the beginning, we're going to study a system without damping, which means we study the ideal vibrating system, something like this, or something like this, only have spring and mass. And once we get familiar with the formulation and the solutions, then we will begin to add additional components and damping, and repeating the same solution procedures, and we see what is the influence of the damping to the vibrations. Okay, so that is our kind of study goal here. This note basically has explained the concept here again. Once we study the system like the vertically involved, and then that kind of gravity here, basically the influence of the gravity will be taken out by considering the equilibrium positions at here. That is where this ends up by following these equations here. Okay, so all the oscillation will be with respect to here oscillating. Okay, so that is these notes we describe here. And for this page, I want to give you the concept about the degrees of freedom. Degrees of freedom defined in dynamics, there's a couple of ways. In traditional dynamics, we define the degree of freedom is such that we have translational degree of freedom, we have rotational degree of freedom. Okay, and translational, both of the kind of translational and rotational degree of freedom depends on the space, say one-dimensional space, or two-dimensional space, or three-dimensional space, depends on the configuration you talk about. Okay, For example, if we consider only a one-dimensional space, then the translation can only happen in that direction. So there's a 1. And rotations only can rotate with respect to that direction. So for this system, we have 2 degree of freedom systems, 1 translational and 1 rotational. Okay. For this one, we have a plane, 2-dimensional. So the translation has, say, for example, in X direction, Y direction, 2 translational. Okay, rotation, and again, you can give the precise constraint or definition. So for example, here you have 1 or 2, depends. And this is the 3-dimensional. So in general, 3-dimensional dynamics, and that is the general case. We have 3 translational degree of freedoms in X, Y, Z directions, as well as we have the 3 rotational degree of freedoms rotating Y, X, Y, Z in terms of the flight dynamics, yaw, pitch, and I forgot the other one.
Yeah. Roll, pitch, and yaw.
Okay, so basically that's 6. Okay, so that's the concept in terms of the traditional dynamics. And in terms of our vibrations, we define our degree of freedom is by the numbers of the mass blocks. So, for example, for this case, we have only 1 spring and 1 mass. So this is called 1 degree of freedom vibrating system. Okay, and because here for this system we only need to use one dependent variable that can be uniquely describe the repeated motion through using X. So that's a 1 degree of freedom. And if we have 2 mass blocks, so let me call this is M1, and then for example they connect to say M2, and for example like this. Okay. So here for describing the motion, the displacement of the mass block 1, I use x1 of t, the function of time, and this is x2 of t. So this is called the 2 degree of freedoms vibrating systems, etc. If there's a more than, you simply count the number of the mass blocks, and that provides you the degree of freedom system. So that is the degree of freedom systems we defined, we dealing with in vibrations. Okay, in the first chapter 5 to chapter 4, I think, 1, 2, 3, 4, 4 chapters are dealing with the 1 degree of freedom vibrating systems. So that means in the first 4 chapters, we're going to deal with the solution process and the physical interpretation of the XT. And then starting from November, I believe, and we're going to deal with the multiple degree of freedom system, and that is combining in chapter 5, that's for 2 degree of freedom, and chapter 6 for multiple degree of freedom. Multiple, that means more than 2. That number can be arbitrary, 2, 3, 4, etc. Depends on my mood, and I can, yeah. And from that moment onwards, sometimes the solution process by hand is very challenging. I would say not hard, but very rigorous, time consuming. So most of the time for the multiple degree freedoms, we go to the programming, for example, using MATLAB for the solution process. Okay, so that is the things we're doing here. And so here is more example here. So that is the one example of the 1 degree freedom systems, and this is the mass block, and this one is a 4-bar linkage, and the mass block is here, okay? And this is a spring, and somehow this motion is confined through this kind of the 4 bars, and this one is typical to that one, okay? And in some kind of drawing, say if you see there's a mass and they can put a kind of small wheels here, this symbol meaning there's no friction between the movement of the mass and the ground. So simply this roller indicating that's a frictionless. Okay. And this one is kind of elastic shaft, and this is the rigid disc with mass. So basically, once we spin a little bit, they're going to back and forth. So basically, this is kind of equivalent torsional spring, and this is a mass. The same concept. Okay. This is an example of the 2 degree of freedom system. We have 1, 2 mass flux. And again, this is rotational. We have 1, 2 initial component. For this one, it's a combined translational oscillation and rotational oscillation. So this is a 1 mass and the second mass. So this is the multiple degree, 2 degree freedom systems. This one is an example of the 3 degree freedom system, 1, 2, 3. And so that kind of telling the degree of freedom is very straightforward. So 1, 2, 3. Okay. And formulations from here, to formulate the equation of motion for this one becomes a little bit more complicated. And so part of the rigors down the road, starting from chapter 5, we're going to have a different formulation approach other than Newton's law. Okay, and we're going to introduce, and that'll be easier for this kind of systems. So.